Hello, hi everyone, welcome back to the channel. So today in this video lecture we're going to be solving this problem, longest increasing path in a matrix. So basically you're given a two-dimensional matrix of dimensions m cross n. It contains integers. We want to return the length of the longest increasing path in matrix. So for each cell you can either move in four directions, left, right, up or down. You may not move diagonally or move outside the boundary. Fine, so let's take an example. So let's see in this example we have a matrix of n cross 3 cross 3, and here in this matrix the longest path would be to start from the second cell of the third row. Now move from 1 to 2, then from 2 to 6, then from 6 to 9, giving me a path of length 4 containing 4 cells or 4 nodes, and hence the answer is 4. So let's see how we can solve this problem. So we want to solve this problem using topological sorting. So let's recall the definition of topological sorting. Basically, topological sorting is a linear ordering of the vertices of a graph such that in the ordering, if a vertex A comes, if there is an edge bit from vertex A to vertex B, then that means A must come before B in the topological ordering. That's the concept of topological ordering. Now, how topological ordering can be used to solve this problem? Let's see that. Now, you can see that topological sorting can be applied over directed acyclic graphs. But here we have a matrix of dimensions 3 cross 3. How can I apply topological sorting, topological ordering for this type of cells, for this type of matrix? Now we can see that we want to find the path, the longest path, such that all of the nodes or the cells along that path are in increasing order. Like in this case, the path is move from 1 to 2, then from 2 to 6, then finally from 6 to 9. We can see that what we can do is we can make edges from those cells which contains lower numbers towards those cells which contains higher numbers or greater integers. Like here in this case we have a cell 2 1, it contains 1. Now we can create an edge from 2 1 to its adjacent cell 1 1, directed from cell 2 1 to 1 1. So there will be a node corresponding to cell 2 1, there will be a node corresponding to cell 1 1, and the edge, there will be an edge from 1 to 6, there will be an edge from 1 to 2, and there will be an edge from this 6 to 8, there will be an edge from 6 to 9, there will be an edge from 4 to 8. Like I will connect all these numbers in the matrix in the order such that each number has an edge, outgoing edge towards the adjacent number which is greater than it itself. Fine, so let's see how we can do that. So let's number the nodes. Let's say for cell 0 0 we have node 0, for cell 0 1 this is node number 1, for cell 0 2 it is node number 3, for cell 1 0 it is node number like for cell 0 2 it is node number 2, for cell 1 0 it is node number 0 1 2 3, and so on. We'll have nodes 3 4 5 6. Let's create edges. We can see that we can create an edge from cell, so this is cell, let's 0 1 2 3 4 5 6 7 8. Create an edge from 7 to 4, 0 1 2 3 4 5 6 7 8. So 7 8. Okay, so from 7 towards 8 there is an edge, from 7 to 4 we have an edge, from 7 to 6 we have an edge. No, we don't have an edge from 7 to 8, we have an edge from 6 to 7 to 6. So this is not here. Okay, so then we have an edge from 4 to 1. Then we have an edge from 4 to 5. Then we have an edge from 2 to 1, because the integer here is lesser than the integer here. Then we have an edge from 3 to 0. So we have an edge from 3 to 0. Okay, then we have an edge from 3 to 0, and from 8 we don't have any edge. From 4 we have an edge towards node number 1 and node number 8. From cell 3 we have an edge towards node number 0, and that's all. From cell 1 we have an edge from 4 to 1 and from 4 to 5. And okay, then from 2 0, from node number 6 we have an edge towards 3. So from 6 we have an edge towards 3. From 6 we have an edge to that's all. There's only one edge from 6 to 3. From 7 we have a edge to 4 and we have a edge to 6. From 2 to we have an edge, like from 8 we have an edge to 5. So from this cell we have an edge towards 5. So from 8 we have an edge towards 5. That's all. So that's the graph that we have. Now here in this graph, the longest path is, if I just find the longest path, that would be starting from 7, it will move to 6, then from 6 it will move to 3, and from 3 it will move to 0. So this is the longest path that I can achieve. Okay, that is 7, 6, 3, 0, containing 4 nodes, and that's the answer. So what I can do is, I can simply find the topological ordering for this graph. So is it okay? Node number 8 has in degree 0. Is there an edge from 4 to 8? There is an edge from 4 to 8. No, there is no edge from 4 to 8. This is wrong. Okay, so this is let's find the topological sorting order for this graph using Kahan's algorithm. So what do we do in Kahan's algorithm? We list first those nodes which has in degree as 0, and those nodes are node number 2, it has in degree 0 here. Node number 8, it also has in degree 0. Node number 7 also has in degree 0, and that's all. These are the nodes with in degrees as 0. Now these nodes are there in the queue, so we push them into the queue. So from node number 2, so we have, like, we push 2, we push 8, and then we push 7 into the queues. Now from 2, traverse its adjacent nodes. So from 2, traverse the adjacent node, that would be node number 1 only. So when I traverse node number 1, this edge will be removed. So we remove this edge, and hence the in degree for node number 1 becomes 1. Okay, now push another node from the queue, that is node number 8. So from node number 8, move to node number 5 and remove this edge. So remove this edge. Fine. And the in degree for node number 5 does not become 0. Now pull the next node, that is node number 7, and from node number 7 move to the adjacent nodes, that will be node number 6 and node number 4. So remove these two edges, that is this edge from 7 to 4 and this edge from 7 to 6. So here you can see that the in degree for node number 6 becomes 0. So that I will push into the queue. Now pull this node from the queue and push it into the ordering. So 6 is there into the ordering. Now from 6, move to the next node, which is node number 3. So remove this edge. And here you can see that node number 3 also has int degree as 0. So push node number 3 into the queue, and then in the next iteration pull out node number 3 and push it into the ordering array. Now from node number 3 move to its adjacent cells, that is node number 0. So put this node number 0 into the priority queue, and so remove this edge, and then the int degree for node number 0 becomes 0, so push it into the queue and put it here in the ordering. So put 0 in the ordering. Now traverse next node, that is node number 4. It also has int degree as 0, so push this node into the queue. This was also pushed when I pushed node number 6. So node number 4 is also there in the queue. Now from node number 4 traverse node number 1 and node number 5. So remove these edges. Remove this edge from 4 to 1 and also this edge from 4 to 5 and push them into the queue. So 4 is out, 4 is here, push 1 and 5 into the queue. Now remove 1, it doesn't have any outgoing edge, and push it into the order. Then remove 5, it doesn't have any outgoing edge, push it into the order. So this is my topological ordering array which I have. Now the next step is I will prepare a DP array where DPI represents the longest path. What it represents is longest path. So this element represents the longest path taken to reach node number I. So let's declare a DP array of size n, where n represents the number of nodes in the given adjacency matrix. So how many nodes are there? Like if the dimensions of the matrix are n cross m, then n into m will be the number of nodes, because these are the number of cells. We have 6 cells here, we have 9 cells here, so there will be 9 nodes numbered from 0 to 8. Okay, so in this fashion we'll have our DP array. Now here in the DP array, let's see that, let's traverse over this ordering. We have 2, 8, 7, so this array is initialized with 1 initially, because all of the nodes contains at least one node, because like I have a path of length 1 which is ending at that node itself. So start from this node, that is node number 2. So for node number 2, traverse its adjacent nodes. So for node number 2, the adjacent nodes are in this adjacency list. What are the adjacent nodes of node number 2? Now we can see that from node number 2 we can move to node number 1, and from node number 2 we can also move to node number 5. So that means from node number 2 traverse node number 5 and node number 1. So node number 1 and node number 5. So that means for node number 1 and node number 5 the length would be 2. For node number 5 it would be 2. Why? Because we can arrive at node number 1 and node number 5 from node number 2. Okay, so it's the equation is like dp of current node on which I am standing, dp node, dp parent plus 1, dp of parent plus 1. Okay, so this will be the dp for the given node. Now here you can see that, like here in this example we had node number 1 and node number 5, and the array for these nodes was updated from like it had like dp of 1 had an answer of 1, and the parent node for node number 1 and node number 5 was node number 2. So for node number 2 we had 1, so it would be 1 plus 1. So max of 1 and 2 would be 2. So for the node number 1 we would have 2, and for node number 5 we would have 2. Okay, because for parent node number 2 we had 1, and while we arrive at the child node we are adding one more node. So in this fashion we'll keep updating the DP array, and finally we'll have our answer stored for like longest path, or the longest path following the numbers which are there in the increasing order. Like in this case, for node number 0 we would have 4. For node number 0 we would have 4 stored. Why? Because node number 3 will have 3 stored. For node number 6 we will have 2 stored, and similarly for node number 1, for node number 7 we will have 1. So from 7 we move to 6, it adds 1 node. Then from 6 we move to node number 3, it adds 1 more node giving a length of 3. Then from node number 3 we move to node number 0 giving a length of 4. So the answer is 4, and we simply return the max element in this DP array. Fine, so this is how we solve this problem. It's just simple implementation of Kahn's algorithm and a little bit of DP. So let's just jump to the code implementation. So let's see the pseudocode implementation. This is longest increasing path function which takes in this matrix. Here we calculate the dimensions of the matrix. Then we declare our adjacency matrix of dimensions equal to the number of elements in the given matrix. So, and we declare a degree array which contains the degree for each node of the cell, or the in degree. Now iterate over each cell of the matrix. Now for each cell we iterate over its adjacent cells. So there are 4 adjacent cells for any given cell of the matrix, and we iterate over its adjacent cells. Like here in this case, for any cell ij, the adjacent cell would be xy, and this dir is an array which is used to traverse to the adjacent cells. Now check if the adjacent cell that we have computed here is valid. If it is a valid cell, then simply create an edge from the parent cell to this new cell, and the parent cell is simply row number multiplied by the number of columns plus the current column. How? Let's say I want to calculate the corresponding node number for this cell, that is node number, that is cell 1 1. Now how many rows I have traversed to reach this cell? 1 row. How many cells are there in each row? We have 3 cells. How many cells I have traversed to reach this cell in this particular row? Obviously 1 cell. So it would give me 3 into 1 plus 1, that is 4. So it's a 4th cell. That's how I'm calculating the node number corresponding to each cell of the matrix. So in this fashion I'm creating the edges, and for each new cell I'm simply incrementing its in degree. Fine, so here I will have my adjacency list prepared, and here I will calculate the order array. So Kahn's algorithm is used to calculate the topological order for this given adjacency list, and this is the degree which I am passing. Now declare a DP array of dimensions n cross m. A DP array, initialize it with 1. Now iterate over this order that we have calculated here, and for each node in this order array simply update the DP as per according to the equation explained here. Fine, and at the end of this function we'll simply return the maximum element in this DP array. So that's all we have to do in this problem. So let's just jump to the code implementation part. Okay, so this is the longest increasing path function. Let's find the dimensions of the matrix. That would be matrix dot size, calculate the number of columns, matrix 0 dot size, declare a adjacency list of dimensions n cross m and a degree n degree of dimensions n cross m. Then simply iterate over each cell of the matrix from 0 to n, then from 0 to m, and for each cell traverse its edges. So I plus, let's create a direction vector. So vector direction vector, it would be 0 minus 1 0 1 0. Okay, so dir plus yj plus I plus, it's not I, it's k, so it's k plus 1. Now check if this new cell is a valid cell. If it is a valid cell, then simply create an edge from the parent cell I into m plus j towards x into m plus y. Fine. And also increment the degree in degree for this cell x into m plus y, because we are creating an edge towards it. Fine. So in this fashion we'll have our in degree array prepared, and here we'll call this function Kahan algorithm, pass in the adjacency list and the order and the in degree array. Fine. Declare a dp array. Size of the dp array is n into m. Initialize it with 1. Fine. And iterate over all the integers in this order array, which is the topological order. Now for each node, iterate over its adjacent cells. Adjacent nodes for this current node, and update the dp array for this adjacent node. For this edge, it would be max of dp of edge, dp, it's dp of edge, dp of it plus 1. At the end, return max element in this dp array. Now iterate over the nodes. We also pass the number of nodes that we have, n, m. Iterate over this n degree array. If n degree for any node is 0, then so iterate over all the nodes of the matrix. Now if the n degree for any node, that would be I into m plus j. If it is 0, then push this node into the queue. So push I into m plus j. Okay, now run the while loop. Pop the node, top node from the loop, from this queue. traverse the adjacent cell for this node, adjacent nodes of this current node. Now, for all the adjacent cells, decrease the in degree for them. So, in degree for the neighbor cells will decrease, and if the in degree for the neighbor becomes 0, push it into the queue. Okay, so here we are popping this node, also push it into the order array. Fine, so that's how the algorithm works, and let's try to submit it. Okay, there's okay, we forgot to pass n and m. Let's see that. I forgot to pass. Okay, we create an edge. Here the problem is that we will create an edge if the we forgot to mention this condition, that if we create an edge only if the cell, the new cell xy, the integer at the new cell, we create an edge from the, if this contains a greater number than the parent cell ij, only in that case we're going to create the edge. So let's now try to submit it. Okay, it got accepted. Let's just submit. Let's see if it is a correct solution. Okay, it got accepted. So that's all. That's all for this video. If you like the video, then hit the like button and make sure to subscribe to the channel. And stay tuned with me for more such content. I hope to see you all in my next video.